I'm Mark Kavanaugh for Cavi Coaches, and today I'm going to coach you up on the 2025 AP Physics 2 exam, FRQs. This is question 2, version J. In this video, we're going to continue the 2025 AP Physics 2 FRQs. This is question 2 on version J. So the question gives us a movable piston inside of a water bath that is held constant temperature, and the piston is movable. It gives us information about the situation in terms of the volume, the area, the mass of the piston, and it tells us that there's a pressure exerted by the atmosphere downward on the piston. The first question tells us to draw a free body diagram, to draw and label, so we can't just draw arrows, but the part that says that each force must be a distinct arrow starting on and pointing away from the dot, which means if we have two forces pointing in the same direction, they both have to start on the dot and be drawn next to each other. So the piston obviously has a force of gravity, so we'll label that capital M. That's the symbol they gave us for the mass, times G. Then we also know that the gas is going to exert a force upward to counterbalance the gravitational force. So the force of the gas is going to push up. But in this case, it also tells us that we have atmospheric pressure pushing down. Now, normally we ignore atmospheric pressure because it's acting all around and all the atmospheric pressure would cancel out on that object because the container blocks the air from applying pressure on all sides like it would in a normal situation. So we only have the atmospheric pressure pushing down, so we have the force of the atmosphere pushing down. So this is our free body diagram. Notice that we have two forces pointing down and they start on the dot and point away, and they should be drawn next to each other as you see here. Now, the next question is asking us to derive an expression for the internal energy of the gas in terms of our given quantities and physical constants. So we're going to begin our derivation by writing a fundamental physics principle or an equation from the reference information sheet. So we just drew a free body diagram, so our best place to start would be to write a Newton's second law equation. So the force of the gas pointing up is going to equal the force of the atmosphere plus gravity pushing down. So those forces up equal the forces pointing down. Now, because it's not in terms of forces, what we're going to do is we're going to convert our forces into pressures. So we're going to divide both sides by area, and we get the pressure of the gas is equal to the pressure of the atmosphere plus mg divided by A. So now we're getting somewhere where we're getting our constants and our given values in our equation. But it's not asking for pressure, it's asking for internal energy. So now we're going to go to our reference information sheet and we're going to find an equation for internal energy. So if you look in the thermodynamics section, you get an equation that says U is equal to 3/2 nRT, or it's equal to 3/2 nkBT. So we have this equation for internal energy where it tells us U is equal to the internal energy. Now, we also have a problem because this equation has temperature in it, and we're not allowed to use the temperature of the water or the gas. So let's find another equation that has pressure and volume as well as temperature in it, which we have PV equals nRT, or it equals nkBT. So you can see that we have two similar equations, one for internal energy, one for the pressure and volume. Now, if it doesn't matter which version of the equation we use, as long as we're consistent in using the same equation. So I'm going to use the nRT version of each of the equations. Now, remember, the problem in the internal energy equation is we have a temperature, and we can't use temperature, so we're going to solve PV equals nRT for temperature. So we get T is equal to PV divided by nR. So now we can substitute that in for temperature in our internal energy equation. So U is equal to 3/2 nR times PV over nR. So you can see the nRs are going to cancel out, leaving us with U is equal to 3/2 the pressure of the gas times the initial volume. So we're almost to the point where we've solved our equation. Now, we can't use pressure of the gas, but we have an expression for pressure of the gas in terms of quantities we're allowed to use. So let's substitute that in. So we have PU is equal to 3/2 times the pressure of the atmosphere plus mg over A times the initial volume. And this is the value for the internal energy of the gas at this specific situation. Now, the next part tells us that we have a block that's placed and it's slowly lowered on, and we're asked to draw a graph of our pressure and volume, so a PV diagram to represent the situation. So let's see what happens when we drop the block slowly on top is that the piston is going to compress. So that means that in this case, the volume decreased. So on our PV diagram, that means we're going to have the volume going to the left. Now, with the volume decreasing, we know that the water bath keeps the temperature constant of the gas. So that means something else has to change. Well, if you have the same number of gas molecules in the container, they're going to collide with the sides more frequently in a smaller container with the same temperature. So that means that our pressure increased. So that means when we draw our PV diagram that we're going to have pressure increasing. So our graph is going to go to the left and it's going to go up. Now, the shape is what is important in this case. And because pressure and volume are an inverse relationship and temperature remains constant because of the water bath, we know that we're going to have an inverse graph drawn for our PV diagram. Now, we also need to draw an arrow. That last sentence says to draw an arrow on your sketch to represent the direction of the thermodynamic process. Well, we just determined that it's going to be left and up. So that means we're going to add the arrow on the end, and we have our PV diagram representing the thermodynamic process when the block is placed on top. Now, part D is asking us, with the block still on top, we now change the temperature of the water bath, which means we're changing the temperature of the gas. And what happens in this process is that the piston moves up so that it ends up back to its original volume. And it's asking us, is the new temperature greater than, less than, or equal to our original temperature? So we need to be able to explain that process. So we need to briefly explain our answer by referencing at least one feature of your answers to parts A, B, or C. So in part B, our derivation for part B, we had T equals PV divided by NR. So that means temperature is directly proportional to volume and pressure. So since the volume increased, that means the temperature of the water increased, and the piston is moving up means that the pressure of the gas is also greater, meaning that the new temperature is going to be larger than the original temperature. Now we probably need to go a little bit further than that because it says to reference our answers to parts A, B, or C. So let's look at our answer to part B, where our internal energy has a direct relationship with volume. So we can see that if volume increases, the internal energy also increases. So that means if the internal energy increases using our equation from the reference packet, that U is equal to 3/2 nRT, that shows that if the internal energy increases, that means the temperature is going to increase also. So referencing our equation that we derived from part B, that the internal energy is a direct relationship with volume, and since volume increased, internal energy increases, and internal energy is also a direct relationship with temperature, so an increase in internal energy means that the temperature increases, also showing why that the new temperature is greater than the original temperature. So this is question 2 on the 2025 AP Physics 2 exam, version J. I hope this was helpful, and I hope you have a great day and an even better tomorrow. If you found this video helpful, click the like button down below, subscribe to my channel, Cabby Coaches, and follow me on Instagram and X at Cabby Coaches.